In this lecture, I will discuss solution to some specific problems from the chapter number 2 of the textbook of Mechanics of Materials by Beer and Johnson, 7th edition. The chapter is about stress and strain under axial loading. I have selected some problems to be discussed in this lecture. The first one is problem number 17 from the exercise. The specimen shown in the diagram has been cut from a 1 by 4 inch thick sheet of vinyl. So it means the thickness of this sheet is, this specimen is 1 by 4 inch. Modulus of elasticity is 0.45 into 10 power 6 psi, and it is subjected to a 350 pounds tensile load, which is shown here. Determine the total deformation of the specimen. So we have to find total delta, and in the part B, the deformation in its central portion BC. In this portion between B and C, we have to find deformation in this portion delta BC. There are total three sections, three portions in this figure, in the specimen actually. Section AB, section BC, and section CD, because the area is changing from point A to point D. There is no change in load. The load between point A and point D is constant, so we do not need to calculate separate load. There is no change of load throughout the specimen, but there is change of area. Since delta depends upon load, length, area, and E. Actually, along the length, if load is changing, or area is changing, or E is changing. E means if the material is changing. So we have to section this the specimen there and find the reaction force. Load is constant from A to B, but area is different between A and B, B and C, and C and D. So if I call it section number 1, section number 2, and section number 3, we have to find a reaction force in each section, which is same in A, B, in section 1, 2, and 3. In section 1, if I draw here, section 1, here is load P equal to 360 pounds. Is it 360? 350 pounds. P is equal to 360 pounds. So P1 will be equal to 360 pounds. Section 2 is between B and C. At NA, we have P equal to 360 pounds. P2 is unknown, so it will be equal to 360 pounds because summation of forces is equal to 0. Similarly, section 3 exists between C and D. Here will be E3, and again it is equal to the applied load. Sorry, this is 350 pounds, I think. 350 pounds. I have to make a correction. Okay, this is 350 pounds. So P1, P2, and P3, all of them are equal to 350 pounds. Now, L1 is 1.6 inches, L2 is 2 inches, L3 is again 1.6 inches. Area 1, area 2, and area 3. area, this is a rectangular area, cross section area, so it will be width multiplied by thickness. Thickness for all the sections is 1 by 4 inches, and width for section AB are section 1 is 1 inch, for section 2 it is 0.4 inch, for section 3 it is 1 inch. So L1 and L3 both are 1.6 inches, L2 is 2 inches, A1 and A3 are 1 into 1 by 4, 0.25 square inch. A2 is equal to 0.4 into 1 by 4. It comes out to be 0.1 square inch. E is same, E1, E2, and E3, all the values of E are same. So here I will write L1 and L3 are equal. They are 1.6 inch each. L2 is 2 inches. Similarly, A1 and A3 both are same. 1 multiplied by 1 by 4, so it becomes 0.25 square inch. And A2 is 0.4 into 1 by 4 becomes 0.1 square inch. Total delta is equal to delta 1 plus delta 2 plus delta 3, deformation in each section. So it will be equal to P1 L1 over A1E plus P2 L2 over A2E plus P3 L3 over A3E. E is given, it is equal to, it is same for all the sections, either for section 1, section 2 or section 3. It is given as 0.45 into 10 power 6 psi. So if we put values which have been already calculated, P1, P2, P3, A1, A2, A3, L1, L2, L3, similarly E, so we can find the net deformation. After calculation, it will be around 25.5 1 into 10 power minus 3 inches. You can do the calculations by yourself. I have already done it. This is part A. In part B, we have been asked to find deformation in portion BC only, between B and C. So it is del 2. In section BC, the deformation is equal to del 2. It is section 2. So del 2 is equal to del BC. It is equal to P2 L2 over A2 E. So put values of P2, L2, A2 and E only, and we can find delta BC equal to 15.5 into 10 power minus 3 inches. It was very simple. First we calculated deformation in the whole specimen, and then in portion BC only. So the whole specimen has been divided into 3 sections, section 1, 2 and 3. We have added up their individual deformations to calculate the net deformation. And section BC is suffering from deformation 2 only, del 2. So it is equal to P2L2 A2 divided by A2 and E. We will move towards our next problem. The next problem is problem number 228. The length of a 3 by 2 inch diameter steel wire CD has been adjusted so that with no load applied, a gap of 1 by 6 inch exists between the end B of the rigid beam ACB. In the diagram, this beam ACB is a rigid beam. It has been pinned at point A and it is hanging with a rope CD with a steel wire CD. Length of the wire is 12.5 inches. There is a weight of 50 pounds resting on the beam. The distance of the 60 pound from end B is x. It means it is unknown. There is a clearance of 1 by 16 inches between end A of the rigid bar and this support E. There is a gap. This beam is in equilibrium. Now, knowing that E is equal to 29 into 10 power 6 psi, E is modulus of elasticity for this steel wire because ACB is a rigid beam. So it is a rigid beam, so rigid materials do not have E. This E is for the steel wire CD. Okay. Determine where a 60-pound block should be placed on the beam in order to cause contact between B and E. So we have to find this distance x so that this beam bends or it rotates. It will not bend because it is rigid. It will rotate around point A so that it rotates and point B touches point E. Here it is written so that it causes a contact between B and E. So we have to fill this gap. We have to remove this 1 by 6 inch gap. So what happens actually, initially this rod ACB is horizontal. It has to rotate around point A and we have to touch it here. Here is a triangle. 1 by 16 inch, we have to fill this gap. At point C, this is point A, this is point B, this is E. If this rod ACB rotates, the point C will shift from C to C dash. It means if the point C has to shift from C to C dash, it has to move down from its current position. It means the rods, the wire steel rod, wire CD has to elongate. The elongation will be equal to CC dash. First we want to find this elongation, delta CD. We can find this elongation using similar triangles rules, using trigonometry. I will move towards solution of this problem. Problem number 228. Here is a rigid bar ACB. It will rotate due to the load. This gap will be filled, which is equal to 1 by 16 inches. AC is equal to AC is equal to 4 inches and CB is equal to 16 inches. This is given in the problem. Okay, we have to find this deformation, which is actually equal to delta CD. So using similar triangles criteria, these two triangles ACC dash and ABE are similar triangles. So the ratio of their corresponding sides must be equal. It means delta CD divided by 1 over 16 is equal to 4 divided by 4 plus 16. So delta CD in triangle ACB divided by 1 by 16 in triangle ABC. This is ratio of two sides is equal to ratio of the other two sides, which is side AC divided by side AB. AB is 4 plus 16. Okay, so from here we can calculate delta CD, and the delta CD will be almost equal to 12.3 into 10 power minus 3 inches. Okay, now we have calculated delta CD. Now I have to find force in the member CD. Why I need to find force in member CD? I will draw a free body diagram here. Free body diagram of this figure. It is like here at support A we have a force RA, and there will be a horizontal force Rx. Okay, RAX and RAY. Then at point C we have FCD, a 50 pounds force is being applied at a distance of x from here. We need to find x. For that, we need to find FCD first. For FCD, we have an expression. I will draw the free body diagram here. Here are two reaction forces, RAY and RAX. Then we have FCD at point C. It is at a distance of 4 inches. Then we have a downward force of 50 pounds at a distance of x from end B, and at a distance of 20 minus x, because the total length is 20, from end A. We have to find x. For that, first I want to find FCD. Del CD is equal to FCD, length of CD, divided by area of CD into E of CD. Del CD has been calculated already. This length of CD is given. It is 12.5 inches. Area of CD can be calculated from the diameter of the wire CD, 3 by 32. It is diameter. And E is also given, which is 29 into 10 power 6 psi. So from here we can find FCD. We will put the values here. 12.3 into 10 power minus 3 is equal to FCD into length is it is I think 12.5 inches. Area is pi by 4 into diameter. Diameter is 3 by 32 square, and E is 29 into 10 power 6. So we can find FCD from here. FCD can be calculated. You can do the calculations by yourself. I will directly write it as I have done the calculations. FCD will be 200.18 pounds. Now FCD is known. I want to take summation of moments around point A. This is point A. I will take summation of moments at point A equal to 0. So if we take moments at A, these two reaction forces Rx and Ray have no moment at around point A. They cannot create any moment because they exist at point A. So we do not need to calculate these two unknowns. Simply, I will write summation of moments at point A equal to 0. This force FCD is producing counterclockwise moment around point A, and the 50 pounds force is producing clockwise moment around point A. So if I consider the counterclockwise moments positive, so FCD into 4 inches minus 50 pounds into 20 minus x inches. This 50 pounds force has a distance of 20 minus x from end A. This sum is equal to 0. So FCD is known already. X can be calculated from here. You can put the value of FCD here, and after calculations you will find x equal to 3.9856 inches. This was required in the problem. We were asked to find distance of this weight of 50 pounds from end B, so that this rod ACB, this beam ACB, which is a rigid beam, it rotates and the end B makes a contact with point E. To make this contact, it has to cover a distance of 1 by 16 inches vertically. If we move from B to E, we can make a point A is fixed. It is a pin support, so it will make a triangle ABE. For that, point C has to move from C to C dash. It means this wire CD has to elongate equal to a distance of equal to a value of delta CD, which is equal to CC dash. We have calculated CC dash or delta CD using trigonometry. After calculating delta CD, we found FCD from the deformation expression, and using this free body diagram, we have calculated the distance x, which is the distance of the load of 50 pound from end B. Okay, now I will move towards our next problem, which I have chosen for this lecture. It's problem number 251. The problem statement is: a rod consisting of two cylindrical portions, AB and BC, is restrained at both ends. We can see there are two cylinders, cylinder A and cylinder B. Both are made of two different materials, and it is restrained at end A and end B and C. Portion AB is made of steel. Modulus of elasticity of steel is 200 gigapascal, and alpha S, it is coefficient of thermal expansion. It is 11.7 into 10 power minus 6 per degree centigrade. And portion BC is made of brass. Value of modulus of elasticity for brass is 105 gigapascal, and coefficient of thermal expansion for brass is 20.9 into 10 power minus 6. It is minus 6 per degree centigrade. Knowing that the rod is initially unstressed, determine the compressive force induced in ABC when there is a temperature rise of 50 degrees centigrade. Initially unstressed means there are no loads being applied and the temperature is room temperature or constant temperature. So there is no elongation or compression in the two rods AB and BC. After we apply heat, there is a temperature rise of 50 degrees centigrade. So the rods will try to elongate, and they cannot elongate because they are restrained at point A and point C. So if we stop the elongation, the thermal elongation, there will be thermal stress. And if there is a thermal stress, it means there is a load. So we have to find that load, that compressive load, compressive force. This is a statically indeterminate problem. We have to solve it using principle of superposition. Problem number 251. In the first step, we have to remove one of the reactions. For example, I remove reaction from point C, which I may call a redundant reaction. I will simply fix it from point A. So there will be a thermal elongation, delta T, due to increase in temperature, there will be delta T. Okay, this delta T is equal to sum of elongations in member AB and member BC due to heat increase in temperature. Okay, it will be thermal elongation is equal to L alpha delta T. So L length of steel portion, alpha of steel portion into delta T is change in temperature plus length of brass, alpha of brass into delta T. This will be the total change in length due to increase in temperature. Okay, length of the steel portion AB is given in the diagram. It is 250 mm. Length of brass is 300 mm. Diameter of steel is 30 mm. Diameter of brass is 50 mm. And similarly, alpha for steel is 11.7 into 10 power minus 6. Alpha for brass is 20.9 into 10 power minus 6. I will put all these values here. Length of the steel, it is 0.025 meters. It was given as 25 millimeters, so we have converted it into meters. 11.7 into 10 power minus 6 per degree centigrade. Temperature is 50 degrees centigrade. Remember that the units of delta T and alpha must be in the same, like both will be in terms of degree centigrades. If one of them is in some other unit of temperature, you have to convert it. Okay, it is 30, length LB is 30, so it becomes 300, so it becomes 0.3. The previous one is 0.25 because it was 250. Okay, 0.3. Coefficient of thermal expansion is 20.9 into 10 power minus 6, and delta T is again 50. So change in length due to temperature, delta T becomes 459.75 into 10 power minus 6 meters. In the next step, I will add the load redundant reaction at NC. Let me add the redundant reaction at NC, which is load P, unknown, and I have removed the heat. There is no change in temperature now because we have already calculated deformation due to change in temperature. Now we will calculate deformation due to the constraint at point C, the redundant reaction. So deformation del P. Okay, load is constant between point A and point C, but area is changing. There is section 1 and section 2. Okay, or I will call it section brass B and section steel S. So it is equal to del in steel plus del in brass. It is equal to P length of steel. P is same for both of them, divided by area of steel to A of steel plus P into length of brass section divided by area of brass section, E of brass section. We will put the values in it. It becomes 0.25 P divided by 200 into 10 power 9 into 706.86 to 10 power minus 6 plus 0.3 P divided by 105 into 10 power 9 multiplied by 1963.5 into 10 power minus 6. Okay. The area has been calculated from the diameters. You can do it by yourself. Diameters of both the rods is given. Okay. This area, here I have directly calculated it from diameters. Pi by 4, pi by 2 diameter square. So you can do it by yourself. Sorry, pi by 4. Pi by 4 into diameter squares. So delta P becomes 3.2235 into 10 power minus 9 P. It is in meters. So we have two deltas, delta T and delta P. Their sum must be equal to 0 because there is no net change in length. This rod ABC is a close fit between end A and C, end and C. So there is no net change in length. So net deformation is equal to 0. So by putting the expressions above, delta T is 459.75 into 10 power minus 6 and delta P is 3.22. 459 0.76 into 10 power minus 6 plus 3.2235 into 10 power minus 9 P is equal to 0. After simplification, we can find P is equal to 142.624 into 10 power 3 newtons, or P is equal to 142.624 kilonewtons. This was required in the problem to find the load or the force, compressive force. Sorry, this will be negative. P will be negative. If you do the calculations, P will be negative. The compressive force required at end C so that this rod ABC is not allowed to expand due to increase in temperature or due to thermal strain. Okay. So we will move further. The next problem is problem 270. Problem number 70 from the exercise. The statement is, the block shown is made of magnesium alloy for which modulus of elasticity E is 45 gigapascal and Poisson's ratio nu is 0.35. Knowing that sigma x, stress in the x direction, is minus 180 megapascal, it is compressive. It is shown here, sigma x. Determine in part A magnitude of sigma y, this compressive stress sigma y, for which the change in the height of the block will be 0. Change in the height of the block, it means delta y is 0 or epsilon y is 0. Part B is, so delta y or epsilon y is 0, we have to find sigma y in part A. In part B, the corresponding change in the area of the face ABC. Where is the face ABC? This top face ABC. We have to find the change in area of face ABCD. And in part C, the corresponding change in the volume of the block, del V, total volume of the block. We have to find del V. Okay. For the first part, problem number 270. Okay, we know that del y is equal to 0 or epsilon y is equal to 0. Sigma z is also 0. There is no stress in the z direction. You can see here. Sigma x is given. Sigma y is unknown, but it has been shown in the diagram. Sigma z is 0. There is no stress shown in the diagram. sigma z is also 0. Okay. Using the generalized Hooke's law, we know that strain in y direction is equal to 1 over E sigma x, sorry, it is 1 over E minus nu sigma x plus sigma y minus nu sigma z. Okay. Sigma epsilon y is 0, sigma z 0. These two terms have been omitted. So sigma y becomes equal to nu sigma x. Sigma x is given as minus 180 megapascal. Nu is given as 0.35 into minus 180 into 10 power 6. So sigma y becomes minus 63 into 10 power 6 or minus 63 megapascals. Minus 63 into 10 power 6 pascals or minus 63 megapascals. So in the first part, we were asked to find sigma y, which has been calculated. It is a compressive force minus 63 megapascals. Okay. In the second part, we are required to find del A B C D. Del A, change in area of surface A B C D. Here is surface A B C D. This top surface. Change in area. For this, first we need to have initial area. What is initial area? Initial area is length into width. Length is this 100 mm. Let me call it length in x direction, Lx. Length in z, width is in z direction, this one. This is Lz. And height, which is not required for area, but it will be required for volume. This is Ly, length in y direction. So Lx 100 mm and Lz 25 mm is required. Before this, we will find strain in z direction and strain in x direction. So I will move. I will find strain in z direction and strain in x direction first, because if the area is changing, area of the top surface ABCD is changed, so there will be change in the length in x direction and length in z direction. First I will find strain in z direction, which is 1 over E into sigma z minus nu sigma x minus nu sigma y. So by putting the values, sigma z 0, sigma x and sigma y are known, nu is known, E is known. If you put the values, it becomes minus 1.89 into 10 to the power minus 3. Strain has no units. Epsilon x, strain in x direction, is 1 over E sigma x minus nu sigma y minus nu sigma z. This is generalized Hooke's law. Again, sigma z 0. By putting the values of sigma x, sigma y, nu and E, we can calculate strain in x direction, which will be minus 3.51 into 10 to the power minus 3. Now we are actually solving part B. Okay, area, initial area of surface ABCD is length in x direction and length in z direction, product of these two lengths. Initial area of this surface ABCD is Lx and L multiplied by Lz. Okay, the new area will be Lx into 1 plus epsilon x. This is the new length in x direction. And the new length in z direction is Lz into 1 plus epsilon z. Change in length in x direction and change in length in z direction. Okay. Lx into Lz, and the product of these terms will be 1 plus epsilon x plus epsilon y, sorry, epsilon z plus epsilon x epsilon z. This last term is actually product of two strains. Strain is already very small number, so their product will be a negligibly small number. So I will omit this term for the simplification because it will be a small number. So net area, change in area del A will be difference of final area minus initial area. So final area is Lx Lz into 1 plus epsilon x epsilon z, and initial area is Lx and Lz. So this changed, if we put the values in this, the answer will be delta A will be, first let me simplify it, it will be almost equal to Lx Lz into epsilon x plus epsilon z. Okay, by putting the values, length in x direction is 100 mm, length in z direction is 25 mm, strains are minus 3.51 into 10 to the power minus 3 minus 1.89 into 10 to the power minus 3. So the change in area in terms of millimeters will be, millimeter squares will be minus 13.5 millimeter square. This is change in area of surface ABCD. Okay, now we have to find change in volume. So volume is three-dimensional. We have to multiply the three lengths Lx, Ly and Lz. This is initial volume. For part C, initial volume is product of the three lengths in three directions. Change in volume will be product of the new lengths Lx into 1 plus epsilon x. This is new length in the x direction. Ly into 1 plus epsilon y in new length in y direction, and Lz into 1 plus epsilon z is the new length in z directions. Now if you simplify this term and ignore the terms which involve product of two or three strain terms, so this v will be simply as Lx Ly Lz into 1 plus epsilon x plus epsilon y epsilon z. I have ignored the terms involving product of the strain terms. Okay, now the difference in volume will be final volume minus initial volume. So final volume is this one, initial is here. If you subtract, if you put the values of Lx, Ly, Lz, epsilon x, epsilon y and epsilon z in this expression, Lx, Ly and Lz are given here. Lx is 100 mm, Ly is 40 mm, Lz is 25 mm. Epsilon x, epsilon y and epsilon z have been calculated previously. Epsilon x is minus 3.51 into 10 power minus 3. Epsilon y is 0. It is given in the problem. And epsilon z is minus 1.89 into 10 power minus 3. You can put all the values and I will just write the answer directly as I have done the calculations. So it will be minus 540 millimeter cube. It means minus means there is a decrease in volume. Change in volume is negative. It is a decrease. I hope you would have understood it, because there is mostly trigonometry or mathematics involved in this equation. The only expression related to mechanics of material is generalized Hooke's law. So if you know how to use generalized Hooke's law to find strains, because the values of stresses are given, so you can do this problem. I will move further. The next problem is Problem number 298 from the exercise. For P equal to 100 kilonewton, determine the minimum plate thickness T required if the allowable stress is 125 megapascals. Okay, this problem is related to stress concentration topic. We have two cases. We have already discussed two cases, which I want to show here again. First one was stress concentration around a hole, and then stress concentration in case of a fillet. So the given problem involves both the cases. There is a hole in the plate and there are fillets, so we will solve it using both the cases, and we will get two values of thickness, and then we have to define which one is the minimum required thickness. The greatest value among them will be the minimum required thickness, and why it will be I will discuss here and discuss it later. First I will solve it using the case of a plate having hole. Okay, for a plate having hole, what we need, this case, we need ratio of R by D, and what is R? R is the radius of the hole, and D is, small d is capital D, thickness of the plate, minus 2 times radius of the hole. Okay, so for our in our problem, radius of the hole is 20 mm and capital D is 88 mm. We can find small d from here. Problem number this is problem number 298. Radius of the hole is RA, which is 20 mm. D, small d, A is capital D minus 2 times radius of the hole. So it becomes 88 minus 2 times 20. So small d is 48 mm. Sorry, 44 mm. Now we have to find R by D ratio. R by D ratio is 20 divided by 44. It becomes 0.45. So we will go to the curve at R by D equal to 0.45. Here is 0.45. We have to find the value of K. So at 0.45, this is K. Here, the K is almost equal to 2.2. So from figure, at R by D equal to 0.45, K is equal to 2.2. And the K is actually ratio of sigma maximum divided by sigma average. So K is the ratio of sigma maximum divided by sigma average. It means sigma maximum is actually given in the problem. It is 125 megapascal, and sigma average is equal to load over area, or it can be written as sigma maximum into area divided by load. Area is actually thickness into width. So in this case, at this end, area is thickness into width, and width here, because it is around a hole, so total width is 28. We have to subtract the diameter of the hole because it will be maximum around the hole. Area is minimum and stress will be maximum. So actually, if we subtract diameter of the hole, capital D minus diameter of the hole, so D minus 2R is actually small d. dA, which we have already calculated. So area is thickness into dA. So we put it here, K is equal to sigma maximum into thickness into dA divided by load. Thickness will be equal to Kp divided by sigma maximum into dA. We know all the values. K is 2.2. P is given in the problem. It is 100 kilonewtons. Sigma maximum is 125 megapascal. 100 kilonewtons, 100 into 10 power 3. K maximum is 125 megapascal, so it is 10 power 6 pascals. And dA, it is already known, it is 44 mm. So 44 mm means 0.044 meters. So thickness becomes 0.04 meters or 40 millimeters. This thickness has been calculated for the case of plate having a hole. Now we have another case, a plate with fillets. So for fillets, above one was for hole. Now for fillet, what we have to do, first we will look at the graph. What do we need? For this case, we need the R by D ratio. What is R? Small r is radius of the fillet. Small d is diameter of the smaller portion. Width of the smaller portion. And then we need D by D ratio. Capital D is width of the greater width portion, and small d is again smaller width portion. So in our problem, first we have to define what is small d, what is capital D. Capital D is 88 mm. I will show you here. Capital D is 88 mm. Small d is this one, 64 mm. And R is RB, which is 15 mm. Okay, small d is dB. We have already called dA for the previous case, so now I will call it dB. It is 64 mm. Small radius RB. RA was the previous radius in previous case. RB is 15 mm. So capital D over small d ratio is 88 over 64. It becomes 1.375. Small r over small d ratio is 15 over 64. It becomes 0.234. So from the figure, now we will go to the figure and find value of K at D by D ratio of 1.375 and R by D ratio of 0.234. R by D of 0.234. 0.234 is almost here, and capital D by small d ratio of 1.375. We do not have 1.375 in the diagram. We have 1.3 and 1.5. So it will be somewhere between these two curves. So we will find K for 1.3, D by D equal to 1.3, and K for D by D equal to 1.5, and then we will use interpolation. Okay. 0.234, 0.22 and 0.2, it is somewhere here, 0.234. For 0.234, if we draw a line here, it intersects these two curves. Curve of 1 point d by d equal to 1.3 here and d by d equal to 1.5 here. These two values are almost equal to 1.67 and 1.75. So K for d by d equal to 1.3, it is 1.67, and K for d by d of 1.5 is almost 1.75. So we have to find K for d by d equal to 1.375. We will do interpolation. It is 1.75 minus 1.7, these two values, divided by 1.5 minus 1.3. This K of 1.75 is at d by d 1.5, and K of 1.6 at d by d equal to 1.3 is equal to 1.75 minus unknown K divided by 1.5 minus 1.375. So how do we do interpolation? This K is unknown at 1.375. This K is known, which is 1.75 at d by d of 1.5. This K 1.6 is at d by d 1.3. This K of 1.75 is at d by d 1.5. So we can find this K, which is equal to 1.7. We have done interpolation actually. If K is 1.7, we will use the equation of thickness. We have derived it previously, this expression. Kp divided by dp sigma maximum. By putting the values, K is 1.7, P is 100 into 10 power 3 newtons, dB is 0.064 meters, and sigma maximum is 125 into 10 power 6 pascals. So T comes out to be 0.0212 meters or 21.2 millimeters. Now we have two values of T thickness. One is 12.2 mm and the previous one was 40 mm. We have to decide which one is minimum allowed thickness. So this one is minimum allowed thickness. This value is maximum, but this is minimum allowable thickness, because among them this plate will be safe for this case, for the case of hole at the thickness of 40 mm, and the plate will be safe for the case of fillet at thickness of 21.2 mm. So if we allow this thickness 21.2 mm, this plate will be safe for the fillet case, but it will not be safe for the hole case. If we allow this thickness 40 mm thickness, this plate will be safe for both the cases. So the minimum allowable thickness is is 40 mm. This was the last problem which I decided to include in this chapter, in this lecture. I hope it will be clear. If you have any query, you can ask me through email. Thank you.